Right, okay, so, well, we've been asked to compute a flux, and we have this Gauss divergence theorem that lets us compute fluxes. Now, specifically, it's asked us about a flux through a surface, which is a boundary. And so that's what allows us to use the divergence theorem. Okay, all right, so let's write that down. S is the boundary of T, and so the flux through S is triple integral over the region T of the divergence of F. There's Gauss's divergence theorem. Yeah? Okay. Okay, well, let's compute the divergence. Conveniently, P, Q, and R are just X, Y, and Z, and the divergence is 3. Yeah. So that's nice. 3 times then triple integral T of dV. In other words, it's just 3 times the volume. The volume of T. Right? And now let's look and see what this thing T is. So T is bounded by these two surfaces. Well, finding the volume bounded by those two surfaces is a double integral problem. Yeah. Right? That's section 4.3, 4.4.
Yeah, so you have to do the parabola here, and then the other one.
That's right. Think about how those two paraboloids intersect, sort of, kind of like that. Yeah, sort of egg-like, right? It's an egg with a ridge. Yeah. Right. And but you can think of that as a double integral over this, over its shadow like that. And in particular, for any given little piece of area, there's a corresponding little piece of volume, and you think about height times area, and it's just a double integral.
Oh. Okay.
Yep.
So I just do like a sort of like circle-ish projection or the XY plane.
Yeah, you have to look and see how these surfaces intersect. So that surface and this surface, they intersect is, where the two z's are equal, and that'll give you a function of x, or an equation involving x and y, and that gives you the boundary of the domain down there.
Okay.
Yep. Cool.